Does it say recording in progress? Does your side say the Zoom meeting is being recorded?
Yeah, it does.
Okay, so I'm just going to start right now. Hello,
Okay.
everyone. It is my pleasure to introduce an esteemed guest, Mr. Franklin Wang. Franklin did his undergraduate in astronomy at UIUC and is now a PhD student at Texas A&M, conducting research on dynamics and morphology of galaxies and supermassive black holes with Professor Jonelle Walsh. Franklin is also a recipient of the Texas Space Grant Consortium Graduate Fellowship. And and interestingly, Franklin and I met in high school, we eventually in university were advised under the same supervisor, Professor Tjonnie LI, who worked on gravitational waves. And without further ado, I will pass the mic to Franklin right now.
Well, hey, Leif. Yeah, thanks so much for having me here today. I'm very, very excited to be here. And actually, today, like I said earlier, I'm just planning on giving a more condensed version of the talk that I gave at HKU. I just wanted to focus a little bit more or less so on the method. I don't want to get too lost in the nitty-gritty of things this time. And just I wanted to highlight the more important key takeaways of my research. So to kind of preface, my research is on supermassive black holes. So these black holes are typically in between 1 million and 1 billion times the mass of our sun, and they can be found in nearly every single galaxy in our universe. So the big question that I'm trying to answer is why black holes and their host galaxies seem to be linked. So, kind of right off the bat, that statement might not seem too weird, but one should try to remember that while despite their names, supermassive black holes, they're actually really, really, really small compared to their galactic hosts. That analogy that I drew, that I love to draw, that I did at HKU and that I do in all my talks is that imagine if this little mole on your arm dictates how heavy your arm is or how quickly the blood in your entire arm flows. Something that small shouldn't be able to dictate the properties of something so big, but we do see that in the context of black holes and their host galaxies. So very briefly, the things that we actually do see are connections in between the mass of the black hole and large-scale galaxy properties, like the galaxy, the bulge, its mass and luminosity. So my research, conceptually speaking, is pretty straightforward. I want to weigh black holes so we have more data points to add to correlations that already exist. Now, there are several ways to make a black hole mass measurement, but the method that I use is known as stellar dynamical modeling. And the basic concept behind this is that mass makes stars move. And we can use telescopes to observe how quickly and how stars are moving just outside that black hole, and then use computational models to translate those stellar kinematics into a black hole mass. We get our stellar kinematics from instruments that we call integral field units, or IFUs for short. You can imagine IFU data as kind of thousands of photos of a galaxy where each photo is at a specific wavelength. This way, when you stack all of these photos together, kind of like what's going on here, if you can see my mouse, when you stack all those photos together, you get a spectrum. And you don't just get a spectrum, you get spectrum at different you get spectra at different spatial locations. So you can imagine each of the pixels in these images as a single spectrum. The spectrum in one specific pixel will tell us how stars in that specific area are moving. And so with these IFU data cubes, we can get a good idea of what large-scale kinematic properties look like rotation in the galaxy or peaks in velocity dispersions. So once we get our kinematics, once we measure those kinematics from our spectroscopic data, we can start generating orbital models. Now, the basic idea behind this is that we establish a kind of model of the galaxy with a unique black hole mass, stellar potential, and dark matter halo. The code, our dynamical modeling code, then starts generating orbits based on these parameters. So on this specific input black hole mass, this specific input stellar distribution, and this specific input dark matter halo. Uh, it will generate these orbits, and from these orbits, we can obtain model kinematics, which we compare to our observed kinematics, which we obtained from our integral field units. And basically, it's just it's very reductive to say this, but what we do is this very intricate guessing game to find the orbital distribution, this orbital model of our galaxy that best matches what we actually observe. And the closest match between our model kinematics and our real observed kinematics is what points towards that final black hole mass measurement. That's pretty much it as to how we actually do things. If you have more questions on how this method works, I did skip over a stage that I feel wasn't too important for this talk. But I can definitely pull up my slides from the talk I gave at HKU and elaborate in things in more detail if you want. But yeah, so I did cut off a lot of the fat, but what I want to focus on now is the what we actually apply this method to use, what we actually do look at. So remember, our key goal is to make black hole mass measurements in galaxies in order to get a good idea of how galaxies and their black holes grow together. So with this goal in mind, my advisor's former group, they conducted a survey to find nearby galaxies that are suitable for black hole mass measurements. This survey was called the Hobby Eberly Telescope Massive Galaxy Survey, or HET Massive Galaxy Survey for short. And this survey used long slit spectroscopy to identify a representative sample of galaxies that have black holes with resolvable spheres of influence. So this galaxy, this survey, sorry, it actually serendipitously stumbled across a class of galaxy that we call local compact relic galaxies. Now, these compact relics are already pretty remarkable. They're all fairly nearby, and they have very high stellar masses for their effective radii. So essentially, they're really, really, really dense. But the most remarkable thing about these compact relics isn't their radii or their mass, it's the fact that they're, well, relics. So local compact relics, they actually very closely resemble these galaxies known as red nuggets. And red nuggets are found in the very early universe at about a redshift of 2. And red nuggets are these small elliptical galaxies that are not forming stars. So we suspect that these local compact galaxies are relics of these red nuggets. Essentially, we expect that most of these red nuggets in the early universe at a redshift of 2, that most of them over cosmic time, they merged with one another to form your kind of standard elliptical galaxies that we see today. So these are your very, very massive elliptical galaxies or your brightest cluster galaxies, which are found at the centers of galaxy clusters. However, some of them did not merge with one another over cosmic time, and they remained somewhat untouched. We say that they're kind of pristine, and this results in the compact relic galaxies that we find in the Hobby Eberly Telescope Massive Galaxy Survey. So I do really want to hammer home the significance of these compact relic galaxies. If they truly are pristine relics of these red nuggets from the early universe, then that means they are invaluable local analogs of high redshift galaxies. Now, their proximity to us allows us to study them in an unprecedented amount of detail that cannot be achieved directly. And by measuring the black hole masses in these compact relic galaxies, we can get a good idea, a good snapshot of the state of black hole galaxy coevolution in the early universe. So as of today, our group has measured black hole masses in 6 compact relics using stellar and gas dynamical modeling. So just as a quick side note, gas dynamical modeling is conceptually similar to the stellar dynamical modeling that I just described, except this time we use nuclear gas disks as kinematic tracers instead of stars. And it does not, so stellar dynamical modeling actually requires the entire galaxy to be measured and to be modeled. But in the case of gas dynamical modeling, we're only looking at a nuclear central gas disk. And so we only actually have to model that nuclear central gas disk. So when we actually look at how red nuggets size up on these scaling relations, we first, so the first probably tightest correlation is the what we call the M sigma relation. So the connection between the black hole mass and the velocity dispersion of the galaxy's central bulge. So just very quickly, the velocity dispersion is a measurement of how randomly stars are moving. If the velocity dispersion is very low, then stars are all moving in the same direction. If the velocity dispersion is very high, then you've kind of got like this very random motion. Things are kind of moving in all sorts of towards all sorts of different places. But anyways, to come back, when we look at how these local compact relic galaxies and their black holes size up on M sigma, uh, we find that they're all actually within the intrinsic scatter. Now, this is actually not that big of a surprise to us. So cosmological simulations has shown that in between a redshift of 2 and a redshift of 0, where we're at today, the velocity dispersion in galaxies should not change much. So seeing all of these galaxies, local compact relics being consistent with M sigma is pretty expected. The thing that I really want to draw your attention to is the luminosity of the bulge and the mass of the bulge, how these size up against the black hole mass. You'll notice that nearly every single one of these galaxies are very large positive outliers from the what's expected locally. So I'll be referring to this. I'll be talking more so about this rightmost scaling relation, which I'll be referring to as the mass-mass relation. Now, one really exciting explanation for this positive offset is that, well, black hole growth precedes galaxy growth. So because we're seeing these positive outliers from the mass-mass relation, this suggests that we have overmassive black holes in our red nuggets and which suggests that black hole growth has finished growing. Sorry, the black hole has finished growing prior to the galaxy's stellar mass. What then happens over cosmic time is that these red nuggets they build up their mass through by undergoing these dry gas pore mergers, allowing stellar mass to grow in the outskirts of these red nuggets without affecting the black hole mass very much. This is effectively shifting these galaxies rightward on this mass-mass plot, and then moving these galaxies towards the intrinsic scatter to what we see, and moving them to within the intrinsic scatter of our local universe. So this is kind of a dangerous thing to say because the conclusion that black holes grew first kind of hinges on two assumptions. First, that all of these compact relics are actually universally positively offset from the mass-mass relation. Now, if these things aren't, then we do have a problem. If we see compact relics, which are more within the scatter, so kind of like UGC 2698 and NGC 384 here, if we see a lot of these compact relics within the intrinsic scatter, then this would suggest that red nuggets actually do have these normal black holes, and that that would mean that not all black holes grew first. However, as I mentioned, as I do want to kind of point out, there are a lot of similarities between these compact relic galaxies and red nuggets, like similar stellar populations. Simulations have shown that these two things can exist kind of after each other. And also, orbital structure suggests that these local compact relics are very similar to these red nuggets as well. But these assumptions do mean this assumption of the fact that while all of these things are actually positively offset does mean that we do have to consider other theories. Now, a second theory, yeah, a second theory is that sorry, let me just check that I'm on the right slide here. Yeah. So a second theory that we do consider is that there is actually higher intrinsic scatter than we do expect at the high bulge mass end here. UGC 2698 and NGC 3384, as I just mentioned, are pretty big proponents of this theory. These two galaxies, they do lie within the intrinsic scatter of the mass-mass relation and suggest that compact relic galaxies might not all be positive outliers. So the more scatter theory is the larger scatter theory is a plausible explanation, given that this mass-mass relation is actually mostly populated with galaxies in between 10 to the 9 and 10 to the 11 solar masses. So mostly, what I want to say is this scaling relation is best populated kind of down here. It is very sparsely populated at this high mass end. This high mass end is where our compact relics lie, this means that this scaling relation is not very well constrained at this high mass end. So it is very, very possible that we just do have a larger intrinsic scatter than we previously expected. So a third theory is that there's actually a systematic difference between stellar and gas dynamical mass measurements. We do find that all six compact galaxies are somewhat offset from the mass-mass scaling relation, but we actually do find that the stellar dynamical mass measurements are further offset than the gas dynamical measurements. So sorry, I should mention that these red measurements come from stellar dynamical modeling, and these blue measurements, they come from gas dynamical modeling. So this is something that other folks in my group have actually been working on, which is consistency checks between stellar and gas dynamical mass measurements. So what I'm showing on this slide here are previous black hole mass measurements for the supermassive black hole in M87. So stellar dynamical mass measurements kind of confusingly inversely to the plot that I just showed. The stellar dynamical mass measurements are in the blue and the gas dynamical mass measurements are in the red. And you'll notice that all the blue measurements are slightly higher than the red measurements. And this is very similar to what we're seeing in our compact relic galaxies. Unfortunately, I don't know enough about gas dynamical modeling to explain why there might be an intrinsic difference. But I do know, what I do know is that we do actually plan to address this discrepancy in our future work. And so that's actually what I believe I will be doing in future work. So just before I actually went back to Hong Kong, something that really helped me adjust to the jet lag was I spent all night looking at this galaxy right here, PGC 11179. I was up all night with the Keck Observatory in Hawaii, and this PGC 11179, we already have gas dynamical measurements. So we already have measurements from the ALMA array down in Chile, and we were getting we're getting IFU observations for stellar dynamical mass measurement of PGC 11179. Point being, plans are in place to conduct consistency checks for all of these, well, to my knowledge, for all of these galaxies with gas dynamical measurements and see if those stellar dynamical mass measurements are intrinsically higher. With all that being said, what we need to do right now as well is to make more black hole mass measurements in red nuggets and in these local compact relic galaxies. This will either support our theory that yes, black holes grew first, or at least help us constrain the intrinsic scatter in these high at the high mass end of our mass-mass scaling relation. And this is where I fit in. So over this past year or so, what I've been doing is constraining the black hole mass in this compact galaxy, PGC 12557. This is the Sloan Digital Sky Survey image of the field that PGC 12557 is in. Kind of small, compact guy. Nothing too remarkable about it, just at a glance. So I have actually finished extracting the stellar kinematics from PGC 12507 and constructing the mass and luminosity models for this galaxy. So just kind of to highlight here are we used the Gemini NIFS, so a IFU on the Gemini Observatory, Gemini North in Hawaii. These are our high angular resolution dynamics. I probe like a 3 by 3 arc second region right outside the center of the galaxy. We do see very nice rotation. So red in this velocity map, red means that these stars are moving away from us. Blue means these stars are moving towards us. This is great. We like to see very clear rotation. The other map that I want to point to bring your attention to is this velocity dispersion map. How randomly stars are moving in the galaxy. You do see this peak towards the center. And that is typically indicative of the presence of a central supermassive black hole. So 2 check marks there. If you have any further questions about these higher order Gauss-Hermite moments, I can explain them, but for now, I'm just going to gloss over them and move on. We also have kinematics from LRS-2, which is an IFU at the Hobby Eberly telescope at the McDonald Observatory out in West Texas. If you're ever in Texas, Leif, I do recommend that you go visit the McDonald Observatory. It's a really, really cool place to go, although it is way out near El Paso, so it's very far out of the way from where I'm at right now. But basically, these LRS-2 kinematics, as you can see from the spatial scales, they do actually probe a larger spatial scale. Instead of this 3 by 3 arc second region that we're probing with our NIFS kinematics, the LRS-2 kinematics, they probe just off the top of my head, it's not a perfect square. I think it's like 8 by 5 arc seconds. But basically, the whole point of these larger scale LRS-2 kinematics, these NIF kinematics, they're probing a small region, so they're really getting a good idea of the stellar kinematics right around that black hole, so within the black hole's sphere of influence. These LRS-2 kinematics, it's showing us more of the galaxy. It's telling us how the stars in this galaxy contribute to the overall kinematics, and that helps us separate the stellar contribution and the black hole contribution to the galaxy's overall gravitational potential. But again, with these LRS-2 kinematics, we're seeing nice rotation, and we're kind of seeing, it's not as obvious, but we do see a peak in the velocity dispersion. Now, last thing I will note is that you'll notice that these red regions are kind of misaligned. That's just a fault on my part. I was too lazy to kind of rotate this kinematic map. But basically, the way we set up our observations is we did have to rotate things a little with the NIFS kinematics when we were actually observing it. But these 2 red regions should be aligned. They're not rotating in kind of different directions when we go to larger spatial scales or anything like that. And finally, here I show the results of a very preliminary dynamical modeling run. So here's a corner plot showing kind of the free parameters we're using. So the black hole mass, of course. This C is a dark matter concentration parameter. This F is a dark matter fraction parameter. And this ML is a mass to light ratio. This is kind of a probe of the stellar mass of the galaxy. And so our very preliminary results are actually showing that the black hole mass is indeed overmassive, just like these red measurements, these red points up here. And this is, it's still too early to say, but just a very preliminary look is that This is giving us more evidence for the fact that actually, yes, black holes did precede the growth of galaxy growth. So to kind of summarize, my research, we looked into the connections in between supermassive black holes and their host galaxies. We do see that these two things are intrinsically linked, but given their difference in spatial scales, this is very, very surprising. We're not too sure why. And what we want to do is make more black hole mass measurements in order to get a better idea. One ga class of galaxy that we actually probe this in are these compact relic galaxies. We suspect that these compact relics are probes of black hole galaxy coevolution at a higher redshift because we think that they might be these relics of red nugget galaxies. Now, current findings suggest that either black holes grew first, excuse me, that our scaling relations have larger intrinsic scatter than we previously expected, or that there's just a systematic difference between gas and stellar dynamical black hole mass measurements. That being said, thank you for your time, and I'm happy to take any questions that you might have.
Hey, Franklin, excellent talk. And I just have a couple questions regarding your research first, and then I'll go to some of the fun questions a bit later. So, one of them is in my research, I require stringent bounds on the supermassive black hole mass to make predictions on gravitational wave signatures and their detectability. I find that typically when you use different M sigma relations, I get completely different mass bounds, which is what you've also shown. Can red nuggets be used to provide a more stringent constraint on the supermassive black hole mass? That's the first question.
Yeah, so that's a really, really good question. And so, okay, so one thing, that's kind of so yeah, like you can see here, there are two different scaling relations that kind of arise from that different samples that people have tackled. And yeah, like you said, I'm sure this does some really crazy stuff to your black hole masses, because I'm assuming your black hole masses, when you're looking at gravitational wave signatures, you're looking more so at the stellar mass end, which is like 100 solar masses and below. Um, so I do want to say that these red nuggets can and should give you better constraints on your on your mass bounds because uh what uh what these red nuggets are really doing is tightening the constraints at a high mass extreme of the scaling relation. So it's not necessarily working in the mass regime that you're working at, but anything that can constrain, that can make these correlations tighter is always good. So like I said, this M sigma relation, it's really only really well defined in between, I would say, this 10 to the 7 and 10 to the 9 black hole mass range. So what we really want to do is tighten this correlation by adding more points to it at this high mass range and the low mass range for that matter. And that's what nuggets are doing.
Actually, I want to say something really quick. So I've actually been working on
Mhm.
visa sources recently. So I've been working in the mass range of more like 10 to the 5 to 10 to the 6. But you just mentioned 10 to the 7 to 10 to the 9. So is it would you say it's quote unquote worse at the lower mass end, like let's say 10 to the 4 or 10 to the 6 solar mass black holes, let's say.
So that's actually I was a little bit scared you would say that because I did kind of guess that yeah, like I am aware of this future search for what are called more intermediate mass black
Mm,
holes
mm, mm,
with Lisa, and from the other folks I've been kind of talking to in the department, it does look like Lisa will be a very premier observatory to detect these sources.
mm,
Um, so. I'm personally more interested in intermediate mass black holes myself, and to kind of answer your question, I don't actually know if it's worse at the high mass end or the low mass end. So, but just a knee-jerk reaction is I do think it is a little worse at the low mass end, given that these high mass black holes, the reason why we don't have that many mass measurements at the high mass end is because these things are relatively rare. But when we do find them, we can pretty accurately make mass measurements of these black holes. These mass estimates are all pretty robust. The issue with the low mass end is that, so one important thing with stellar dynamical mass measurements is that you really need to be able to resolve the sphere of influence of that black hole. And uh, so with these lower mass black holes, you have, you know, the whole short shield radius equation. You know that that short shield radius, it scales with the mass of the black hole. So with these lower mass black holes, you have smaller spheres of influence, which are a lot more difficult to resolve, at least with our current generation of telescopes. Now, in the next, ideally, 10 years or so, which I really hope so, because that would be really good for my career. These extremely large telescopes, they're going to come online and they will actually grant us the ability to resolve these smaller spheres of influence. So the spheres of influence, these 10 to the 4, 10 to the 5, 10 to the 6 solar mass black holes will have. But fact of the matter is, at the stage we're at now, these things are pretty much impossible to resolve. So stellar dynamical mass measurements are if not difficult, then they're completely impossible, which forces us to rely on not measurements, but probably these correlations to actually predict that black hole mass. And so things down here are probably a long way to say things down here are a lot more uncertain, given that the methods that you're using to measure those black holes are a lot less precise.
Another question I think was I don't remember the answer when someone asked you this question in the talk back at HAU. I remember someone asked something about the orientation of when you're viewing the galaxy and if there are challenges if you're looking at it face on or edge on. So I could you elaborate that a little bit on that really quickly? Yeah.
Yeah, so that's a really good point, and that's actually the part that I cut out of
Yeah.
this talk I'm giving today. So um one thing that we do have to consider is the so in the most simple case, when we're modeling these galaxies, we model a completely spherical galaxy. So the angle at which you're looking at it's a ball. It doesn't matter at all. But as you may have guessed, a spherical galaxy is probably not physically realistic unless you're looking at, say, a globular cluster or something like that. Um, so in the next slightly more simple case is a axisymmetric galaxy. So now here we're really talking about like the morphology of the galaxy. In the case of an axisymmetric galaxy, we're assuming that the galaxy is symmetric about one of its three axes. So the only angle that we kind of need to take into account is the inclination angle. So which way it's kind of tilted towards
Uh,
us.
so basically it's
So
either
in
like a circle or like it could be more elliptical if you look at it face a little bit. Okay, I see. I agree.
Exactly, yeah. So in the case of PGC 12557, so this galaxy that I'm looking at, we're actually assuming that it does have a fixed inclination angle. And I need to go back and double check what the angle is, but it is closer to being edge on than it is to being face on towards us. Now, the third and more intricate scenario is that I just talked about axis symmetry, where we assume symmetry across a single axis. And so in that case, we only have to consider one angle. There is a third, more complicated model, uh, which is called triaxiality. So in this case, we allow all the axes of this galaxy to kind of vary, and this is probably our most realistic situation. But in this instance, you do have to consider not one but three viewing angles, and that really, really complicates things. So with our axisymmetric models already, things take a very long time to run. With our triaxial models, instead of just like three free parameters in our models, you're adding an additional three. So you're modeling six free parameters in total, and things take a really, 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 really long time. We do have the code that does it, but it is very computationally expensive and it does take a very long time, but it is our most accurate way to get a supermassive black hole mass measurement.
Oh, okay. So there's another question. Can you go back to the slide where you show uh plots with the Gauss-Hermite moments? It was
Hmm.
yeah, I think it was the one at the end. Yeah,
This one?
yeah. I think you said what is you kind of skip what is the in kind of the interpretation of the higher order one. So I don't know if you could elaborate a little bit on what are the well, you put the plot here for a reason in the prep, right? So what are the kind of the significance of plotting these higher order Gauss-Hermite moments?
Yeah, so kind of just to briefly preface, so each of these different colored regions, they're a spatial bin.
Mhm.
And in so these galaxies are far too distant for us to actually be able to measure the movements of individual stars. What we can do instead is measure a distribution of how stars in this galaxy are moving. So in this spatial bin, imagine kind of a Gaussian.
Mhm.
Uh, say this bin is red, so the peak of this Gaussian is about at 180 kilometers per second. In the same bin, the width of this Gaussian is about 270 kilometers per second. That's the measurement of velocity dispersion. And then these higher order Gauss-Hermite moments are kind of it's very hard to describe what they are physically, but in terms of that Gaussian that I was talking about, so H3 is like where that Gaussian is kind of skewed. This H4 is how sharp or how flat the peak of that that Gaussian distribution is. And then I'm not too sure what H5, H6, H7, H8, and so on are, but we can measure those too. But the physical significance of these higher order Gauss-Hermite moments is actually it's to kind of shatter this degeneracy. So we do find that there is a degeneracy between the black hole mass and the orbital anisotropy of these galaxies. So we find that in our dynamical models, you can produce very well-fitting orbital models that come from a model with a black hole. So that's great. We're trying to make a mass measurement of the black hole. If there is a black hole present, it can produce kinematics that very much so look like our observed kinematics. Another scary possibility is that we can actually take that black hole away and have a very radially anisotropic orbit. Sorry, we have very radially anisotropic orbits with no black hole, and this actually also closely reproduces our observed kinematics in a lot of cases. So what these higher order Gauss-Hermite moments do is the more Gauss-Hermite moments we have, the better we are able to actually get past that degeneracy. So we actually find that these two things, these two different models look like each other when we only measure the velocity and the velocity dispersion, and this anisotropy is easier to break. I guess it's easier to reject the anisotropic model once we have more and better constraints of these higher order Gauss-Hermite moments.
Ah, I see. Okay. So it's very similar to the technique used in statistics. So if you don't have if you have very low sample, not in this case, it's not low sample size, but they take higher order moments to understand the your data set a little bit better. My last
Yeah.
question, yeah, the last question I kind of want to ask is more general for this kind of research. So, uh, I I know that the main kind of idea is to just talk about the mass of the supermassive black hole or the does these measurements with red nuggets, do they yield any other physical information about the galaxy apart from the mass of the black hole, let's say? Yeah, I did mention spin in my in our talk at HAU, but the problem is spin is much more difficult, so I don't really want to get into that. So are there any other properties of these galaxies or supermassive black holes that can be measured, let's say, with these red nuggets?
Yeah, so we do actually measure uh although it is not really the focus of my research, we do actually look at the stellar mass distribution and the dark matter halos
Oh.
in this galaxy. So as for the dark matter halo, one thing that another person in our group is actually working on is they're using these same kind of dynamical models, except to look at more so the dark matter content in galaxies. So one big question is that we face in research today is, uh, what is actually the dark matter fraction of massive galaxies? So we do see at the kind of the dwarf, the lower mass end, we do see that those galaxies are more dark matter dominated. And then kind of preliminary results is we're seeing kind of a parabola where you get to this kind of dip in like I think it is around like 10 to the 10, 10 to the 9 solar masses. Those galaxies have less dark matter content. And then as you get to the higher end, so 10 to the 11, 10 to the 12 solar mass galaxies, you see the dark matter fraction slightly going up as well. I don't want to say too much more about that because that's not really my expertise. I just kind of know it is kind of uh, an area of research. As for the stellar mass, it's just kind of good to get an idea of like how these things are kind of how these things are kind of set up. So we do find that these local compact relic galaxies, it is good to just know like that they are indeed compact. From these dynamical models, we can measure their radii, how quickly things drop off, and other structural properties of the galaxy.
So that's all for me from the research questions. I'm probably going to
Cool.
ask maybe one or two let's say fun questions. It's I guess the first one is in your field. Uh I get asked all the time what kind of resources did I use to get into my field and what resources I use regularly. So I want to ask you kind of the same question. So let's say when you're doing observational astronomy and you're doing work on data analysis, what kind of resources do you use and what kind of I guess some kind of advice that you would give people who want to get into your field. That's one.
So that's a great question. I remember actually when you and I, when we were applying to uni, I did remember seeing a article in the South China Morning Post of how actually HKU scrapped their astronomy major, and that HKU was the very last university in Hong Kong to actually have that astronomy major. And it was saying like, oh, what if the next Carl Sagan is born in Hong Kong and they want to pursue astronomy and and basically we're screwed. There's actually not going to be any route for people interested in astronomy to actually get into astronomy.
Mhm.
So I actually think I want people to kind of like scrap that mentality. I think a physics major is it is more than adequate for you to actually get into astronomy research. So yeah, one big fear I did have applying to grad school was actually, oh, I'm not a physics major. I'm not going to have the coursework and the mathematical preparation necessary to do astronomy research. And I'll explain later why that actually wasn't the case. But like for undergrads who want to sorry, for high schoolers who want to get into astronomy research, if you are limited to that physics degree, don't worry about it. That is completely fine. And that's actually what, even in the United States, that's what most people have. An astronomy major is actually only really offered in maybe 30 institutions across the United States. And in the vast majority of those times, um, People usually do pair that with a physics major, and like most of the people in grad school today are actually they do. I actually wouldn't say most. A big chunk of the people do come from pure physics backgrounds. Now, as for the people, I think this is a much smaller group of people, like myself, who only did astronomy majors instead of majoring in physics as well. I would recommend that you do actually take those harder physics classes. So not like those introduction to mechanics that you take in your first or second years. I do recommend you take like upper level classical mechanics and upper level E&M and upper level what are the big four? E&M, classical mechanics, quantum mechanics, and
Ah,
probably
that makes sense.
thermo
Yeah.
and
Yeah.
statistical mechanics. Yeah. I do recommend that you take those. So it proves to grad admissions committees
Mhm.
that you can handle the grad level coursework. But besides from that, don't worry too much about it. I actually use very little maths in my day-to-day work. What I do recommend is you actually do learn how to code. I think that is really more important.
I completely.
As yeah, like I think yeah, I code every single day. It's something you like, people say go do these like Khan Academy things, and I think those are helpful, but like really what you should do is just like get as much experience with it as you can. That's the only way you're really gonna learn. Kind of a last thing, I know, sorry, I do ramble a lot, but
Well, it's all right.
the
Yeah.
thank you. Yeah, but as for research, people who want to get into research specifically, uh, all I gotta say is you gotta get on your knees and you gotta start begging. You gotta start asking as many people as possible. So like I remember when before I started working with Tjonnie at CU, Tjonnie was about the 10th or 11th person I emailed at Hong Kong. I think I emailed pretty much every single faculty at HKU, like saying like, hey, please take me, like I'll do anything for you and I'll do it for free, you know.
Yeah.
And I was contacting a lot of people at CUHK as well. There isn't really one at UST that does astronomy research, so I didn't really contact anyone there. But yeah, it was only until I didn't actually contact Tjonnie directly. It was I don't remember his name at CU, but I contacted him and he was like, "Ah, you actually probably want to send an email to Tjonnie," and so I did, and Tjonnie was like, "Yeah, like I'll take it." And I was like, like thank God someone's gonna have me. But like as for getting into research, it does really suck. I'm not going to any way you slice it, it does really suck, and you do have to ask a lot of people. But hopefully, someone will take you on.
I don't know. I make this kind of analogy that doing research like is kind of like going on a date. You have to kind of try things, and then eventually, when you get into grad school, you're gonna have to, in some sense, commit. Like in some eventually, and then maybe for some time, and then when you do your own when you become a professor, you might you could call that getting married, but it's something I analogize it when I tell my undergrads doing a research, getting experience is just like going on a date. And
Oh no, yeah, and
yeah,
I actually completely agree. And it's like this is kind of a really bad way to take this analogy, but one
yeah,
thing I will want to say is that everyone wants to date a supermodel, but not everyone can date a
yeah,
supermodel. And the same
yeah,
kind of thing is with research.
yeah,
Which kind of sucks because like one thing I really wanted to do was exoplanets, but
mhm,
the big issue is that everyone and their mom wants to do exoplanets. So that field of research is actually super competitive,
mhm,
and
mhm.
it is going to be a lot harder for you to get into. And like, I know it's kind of the same thing with the physics side, at least my broad understanding of physics research fields, understand that high energy theory is extremely cutthroat to get
Yeah,
into. So
yeah.
yeah, it's just like everyone wants a date supermodel, but sometimes you have to accept that you probably aren't going to be able to date a supermodel.
Yeah, I think I really like that analogy too. Like the way that you
Yeah.
say it sounds, in some sense, it sounds quote unquote terrible, but it's kind of true.
Hmm.
Yeah, but I don't know. There's another thing that I kind of want to ask. It's a little bit on the research side. So there's a lot of the things students get pressured to publish a lot, and I think a lot of us try to work in kind of hot topics, and sometimes it's not I guess in some sense, sometimes it's not what we really want to work in. I don't know if you have any opinion on that. So some people are working on really hot topics just for the sake of their career. So it's, yeah, I don't know. Do you have any like thoughts on that kind of that not avenue? I don't know.
I actually, this is going to be a very strong statement, but I actually really hate that kind of mentality because I
I do
think,
too. Don't worry, I do too. I'm just asking
yeah.
you. Yeah.
So one thing that I think a lot of people do forget in this field is why they're actually in the field.
Mm.
And let's be honest, if you're getting into physics, if you're getting into astronomy for money, you're an idiot. This field does not pay well. It is very high risk, very low reward, monetarily wise.
Mm.
I think you should be in this field because you like what you do.
Mm.
And I think you should be researching the topics. If you are allowed to research any topic you want, you should research the topics that interest you and that make you happy. You shouldn't like I'm not gonna lie with you. I did not like my time with gravitational waves. I thought it was too mathematically challenging for me,
Mm. Mm.
but it is a much harder topic than what
Yeah.
I'm working on right now.
Yeah.
Do I force myself to work on gravitational waves or do I do something I actually enjoy? And I'm going to do something I actually enjoy, be really good at what I enjoy, and hopefully carve a career out of that, as opposed to forcing myself to do something, to swallow and eat something that I really, really hate just for the sake of, easier career path, you know?
I kind of tell this to people that I have this analogy that following a hot topic is kind of like following a social media trend. You may
Hmm.
not like it, but sometimes you have to do it to get quote unquote the most views, the most likes, blah blah blah. And it doesn't. I analogize research is kind of like being an artist. You want to kind of you want to produce a piece of work that you are happy with instead of following a trend that other people are doing. Yeah.
Oh
I
yeah,
guess I've
100% agreed.
I kind of have just one final question before we depart. So, I think recently, there's been a no in the Nobel Prize. There's kind of been a drought in astronomy. So I was going to ask, what do you want to see to be the next Nobel-winning discovery, or maybe just a discovery that in astronomy that you want to see in your lifetime? In maybe it can be in your field, it can be in any other astronomy field. I don't
Mm.
know. It's, for example, for me, I will hope to see, um, let's say with Lisa, I hope when they launch Lisa out there, there will be discoveries of gravitational waves of supermassive black holes, or maybe some extreme mass ratio and spirals, something like that. So I don't know with your side if there's anything that you want to see, basically. It's a tricky question.
Knee-jerk reaction, aliens. I want to see aliens. I want to see some signature for life outside of our outside of Earth.
Yeah.
I think that would be really awesome. And actually, I don't know if you've been keeping up with some of the James Webb Space
Okay.
Telescope findings. I don't remember exactly what element it was, but with the James Webb, they were actually looking at these exoplanet atmospheres, and they were allegedly finding these molecules that are can only be produced by carbon-based life forms, which I think is like this is incredible, you know.
Yeah.
But as for the like something in my field, something that I'm personally more invested in is definitely I want to see with the new generation telescopes, so these extremely large 50 meter, I don't know how big they are, but like these really, really big ground-based telescopes, I do want to see more robust mass measurements of these intermediate mass black holes because I don't know if you how much you know about this, but we don't really know where supermassive black holes come from,
Yeah,
and
that.
a lot of yeah, and like we do suspect that intermediate mass black holes that they are this kind of missing link that they will tell us a lot about where these supermassive black holes come from. And given that nearly every single galaxy in our universe has a central supermassive black hole, I think it is really important for us to understand where they come from. And I really hope to get that really robust measurement of an intermediate mass black hole.
Yeah, I think that's a very good answer because a lot of the times I see a lot of talks when people come, it's like they say, oh, one key problem in astronomy is we don't know what I don't know if it's source, but how supermassive black holes are formed. It could be through collisions. It could be I don't think accretion is the most likely
Yeah.
explanation, but yeah, those kinds of models. So yeah, I think that's a really those kinds of questions are really interesting. And I think since you talked about aliens, next time you come to Hong Kong, you should definitely meet one of my colleagues because he's really into aliens. So his name is Amruth, and he works on dark matter. So he was really into this alien thing. So next time you come, I guarantee you should talk to him.
Excellent. I love to.
Yeah. Okay, so I think that's the end of this talk, and I thank you so much for agreeing to do this. It's been a pleasure talking to you, Franklin. Yeah.
Yeah, thank you so much for having me. This was a really great time.
Yeah. Now I'm just going to stop recording, and then I'm just going to just
Okay.
chat. Just do that.